Let's discuss about diodes. Diodes are a non-linear circuit elements used in variety of applications such as rectifiers, logic circuits, etc. These are the basics and simplest semiconductor devices. So let's look at uh, the circuit diagram and the symbol for a diode. So diode is basically represented by a symbol like this. This is the this is the anode terminal. This is the cathode terminal. Plus minus, and the current in positive direction flows in this direction, IT, and the voltage is here VT. Diodes are basic can be of ideal type or semiconductor type, like the practical diode. So the ideal diode has a transfer characteristic like this. If this is a current across the diode ID and the voltage across the diode VT, then initially when the voltage is negative voltage is applied, the diode is in cutoff mode. So no conduction happens and the current flowing across diode is zero. And as soon as the voltage is slightly increased towards positive, the infinite current flows through the diode. So this is a ideal representation, ideal characteristic. What happens in practical circuits is that we have a diode is a PN junction type. Basically, there is a P type semiconductor and an N type semiconductor. This is just for explanation. This it doesn't happens like this, and this is for explaining just. And a junction is found here. This PN junction uh, acts as a diode. So practically, the diode has characteristics like this. In forward region it is like this, and positive voltage, and for negative voltage it's like this. This is IT and this is VT. Practical diode, when the voltage increases up to a certain voltage called knee voltage, the current increases slowly. As soon as the forward voltage reaches V knee, the current starts to rise exponentially. And in the reverse region, we can see that this current is very small. This current is very small, and it's suppose if forward in forward region its range is in milliamperes, then in reverse region its range is in nanoamperes or microamperes. So when the voltage across the diode is further reversed and increased, then up to a certain point current is very small, but as we see that here, after reaching a certain point called V senior knee, the current across the diode start increasing rapidly. This happens because of the breakdown in the diode. And two phenomena are basically responsible for this. One is avalanche effect, and another is the Zener effect. In avalanche effect, what happens that due to the reverse bias potential, the carriers moving across these PN junctions acquire so much of the kinetic energy that they hit the crystal ions in the transition region. This is a transition region, and they dislodge the electrons and holes from this, which further uh, participate in this process, and an avalanche of electrons and holes is created, which increases the current across this diode. So this value can be made further low by increasing the doping in this p n junction region, p and n regions. So means this vz can be brought towards more this side. And when and that happens because of Zener effect. As the doping is increased, the electric field potential increases very much in this transition region, due to which the electrons and holes are torn apart from the covalent bonds in the crystal ions, and this increases the uh, electric current. Let's look at some applications of a diode as a half wave rectifier. Half wave rectifier. Here is an AC voltage source, and I connect a diode and a resistor across it and take the output voltage across the resistor. So if the input signal is like this, and a sinusoidal signal of one cycle, then corresponding output signal for one period will be when the diode is positive, uh, it is V input, and here let's plot V output. So when the diode is forward biased, this diode will act as a short circuit. So equivalent circuit will be can be represented by this. So we see that V output will be equal to V input for the positive half cycle of this input voltage. But as soon as the voltage across the diode is reverse, means this anode voltage is less than cathode voltage, or input voltage is a negative half cycle, the diode acts as a open circuit, and it thus voltage across this resistors becomes zero. So we draw the equivalent circuit diagram, and here we have an open circuit. V output, so we see up to this point we have a 0. Continuing in this way in further cycles, it will be again like this, and this goes on. So if average is calculated of this cycle, then we can get almost a DC signal after using proper rectification. We see that this diode can be used as a half wave rectifier also. Next we can see the application of diode and as a logic gate. If I have this type of circuit, I want to draw an OR gate. I have three inputs, and these inputs are connected to the cathode of diodes. So we have VA, VB, and VC, and all the anodes of the diodes are joined together and connected across a resistor and grounded, and output is taken at this point, V output or Y. Let's call this output Y for logical sense. Then we see that whenever a voltage across A is higher, means positive, this diode is forward bias. In logic circuit we use generally plus 5 volt for plus 1, or and 0 for minus 1. Then this positive voltage will cause this diode to be forward bias, and this 5 volt will appear across this point Y. So Y will become 1. Similar, and if others are 0 or 1, it doesn't matter. Similarly, we can see for VB also, if it is forward biased, VB is plus 5 volt, then this is become forward bias, and voltage at this point will be 1, sorry, 5 plus 5 volt. So we see that the equivalent logic becomes y is equal to either A is high, or B is high, or C is high. So we have a OR gate here. Next we can see how the diode can be used to make an AND gate. So we can reverse this thing, and we have a plus 5 volt here, and diodes are connected in this fashion. VA, VB, and VC. And we have a VY here. Whenever a voltage across any VA or VB or VC becomes zero, then this diode will become forward bias, as this voltage at cathode is plus 5 volt. So if any one of them becomes zero, then output will become zero, because it is forward bias, it is zero here, so it will be a short circuit, and we can get V by S 0. So all must be ones. In that case, if VA, VB, and VC is 1, then all these diodes will be reverse bias, and this we can be replaced by open circuits. So, and we have a voltage of plus 5 volt here. So we can see that Vy follows the law of AND gates. So Vy is equal to A and B and C. So we got an AND gate here. The current voltage relationship of a diode is represented by Shockley's equations, and it denotes how much current will flow across a diode for a given voltage across it. So it is represented by I is equal to Is e raised to power Vd by eta Vt minus 1. So if let's say this is ID, current across diode, voltage across diode, and so here Is is saturation current or scaling current. It depends upon the geometry of the of this junction and the doping levels, and it is independent of the voltage applied across the diode. It's due to minority carriers flow across this junction, and Vd is the voltage across diode. Vt is thermal voltage. Vt is thermal voltage, which is given by relation Vt is equals to Kt by Q, where K is Boltzmann constant, and Boltzmann constant. T is absolute temperature in Kelvin, and Q is the magnitude of charge on a single electron. This is 1.6 into 10 raised to power minus 19 coulombs. So at a room temperature of about 25 degrees C, we get Vt equal to 25.8 millivolts. So some authors take it to be approximated to be 25 millivolt, and some to 26 millivolt, depending on their convenience. Some interesting fact about Is is that it doubles for every 10 degrees rise in temperature. It doubles for every 10 degrees centigrade rise in temperature, and it's directly proportional to junction area. If we double the junction area, then this saturation current across this diode will double. Now this, as we see, we have a voltage and current relation, so we can define different type of resistances across this diode. So we have three types of resistance. First is diode DC resistance. DC resistance. It is defined as our resistance at any point on the characteristic curve of the diode. Suppose if this is the characteristic curve, then if I take any point here, there will be some value of current here, ID, and voltage across this diode VT. Then DC resistance RDC is equals to, simply I take the ratio of instantaneous value of voltages and current, so I get this uh, DC resistance. Next comes the AC resistance, and this given by RAC is delta VT upon delta IT. It is measured from a point to point to change in voltages and current. So let's take the forward characteristics here, and if I say uh, if I take a point and draw a tangent at this point, this tangent is this tangent at this point, then let me choose the different pen. A tangent at this point, and this represents a change in current, and this represents a change in voltage, delta VT. So the magnitude of this slope will give the AC resistance. And lastly, we have a average AC resistance. R average AC, and this is a different bit, as if I take these 2 points, if I take 2 points, this point and this point on this curve, and join them, I get a line here, and this slope will give me average AC resistance. This slope, 2 points on this curve will give me an AC resistance. So it is defined in this way. This average resistance is delta VD upon delta ID, point to point. This AC resistance we saw here, it is calculated at a quiescent point of the diode. On doing further derivation, we get the value of this average AC resistance RD is equal to 25.8 millivolt upon ID, the diode current. This relation can be used to find the DC resistance, and it is derived from by this differentiating these shockless equations. So we come to this value for AC resistance. In order to analyze various circuits in which diodes are placed, we have developed certain models to replace a diode. So these models are three types, and first one is piecewise linear model. piecewise linear model. So in this model, a diode in the circuit will be replaced by an equivalent voltage, a resistance, and an ideal diode. This is ideal. This voltage drop represents 0.7 volt voltage, which generally for silicon diodes there is a 0.7 volt knee voltage drop, and this is the RDs. This is the diode resistance that we saw. This has a very small value. The next model is simplified model. In this model, the diode, this junction diode, silicon diode, or practical diode, whatever name we call, it is simply replaced by this voltage source and this ideal diode, 0.7 volt, and this is ideal diode. We ignore this resistance in analysis. And the third one is ideal diode, and here we simply replace this junction diode by an ideal diode. The choice of these models depend upon the application that we are interested to analyze. Looking at the characteristic curves that will come when we choose these different models. So for a piecewise linear model, we will have a curve, something. Draw for others also. For piecewise linear, we'll have a model like this. This is up to Vk or 0.7 volt. Call this Vk also. And for simplified model, we have this type of curve. It is Vk, and for ideal diode we have already seen the curve will be like this. Transfer characteristic curve will be like this. The reverse bias characteristic of a diode is often employed to design a special type of diode that is used as a voltage regulator. So we saw that as the negative voltage across this diode is increased, this current remains very low for up to a certain voltage, and as certain new voltage is reached, then current starts to increase exponentially, and this voltage is given by V set K, and so this region is called the Zener region of operation. This region, and the Zener diode that is specifically designed to operate in this region has this type of symbol representations. This is plus minus V, and the current is in this direction. So this is V set. So as the voltage is greater than V set K in negative direction, this sudden rise in current will be there, but the voltage across this diode will remain constant. So this Zener diode can be used as a voltage regulator in the circuits, and drawing the equivalent circuit symbol for V set K, we get something like this. This is R set, and this is Vset, Vset K, plus minus Vset. This current flows is I signal. What happens is that this Rz, the Zener resistance, is the slope of this curve at the operating point of this diode. For, for a particular given voltage or a current, there will be this point of operation, and at this point the slope is defines this value of Rz. So Zener diode should not be operated in low currents region, it should be operated always for higher current region, as the magnitude of this slope is very much for the low currents. So Rz has a high value for low currents. So it is advisable to operate this diode in the high current regions. We will later see the practical use of Zener diodes in solving these problems, how much there will be the current or voltage in the circuits and the power dissipations, etc.